Oh, okay, it's possible. Yeah.
Can you see?
Yeah.
Okay, perfect.
So just a moment. Yeah.
Mm-hmm.
And after 14 minutes, I will say 1 minute. 1 minute left. So just a moment. I start the stopwatch. Yeah. Okay, you can start. Yep.
Okay. Hello, everyone. Today, I will be doing my presentation on causes of preventable deaths by age. And so my data is on the causes of preventable deaths by age in the US from 1999 to 2021, and ages ranging from 0 to 99. And these causes include deaths by poisoning, motor vehicle, falls, choking, drowning, fire, flames, or smoke, and mechanical suffocation. And we'll only be analyzing the years 2000 2020 based off of the data from the NSC website. The average number of preventable deaths in 2020 was 2001, with a spike from ages 21 to 67. The objective for today is to analyze preventable injury-related deaths by age and the causes in the US, and comparing each of the causes of deaths by age between 2000 and 2020 using line graphs and summarized data for both of the years. Then after that, we'll analyze the relationship between the age and the cause of death by using regression analysis. And after that, we'll be investigating the relationship of changes over time by ANCOVA. And this is a summarized or a shortened version of the data itself. And here is a, something's in the way. Okay, here is a, the line graphs comparing the causes, the age and cause of death between the 2 years. And then the mean is, as you can see, can you see my pointer?
Yes.
Hopefully, okay. It's on the far right corner of each of the line graphs. And for motor vehicles and chokings, there's not really much of a change over time, just some disparities between the two. And then for the falls and poisonings, there's definitely a significant change over time, where poisoning has, from ages 20 to 60, there's a huge spike, and same with for falls, ages 60 to 100, probably due to population growth. And then similar situation, drowning and fire, flames, or smoke and mechanical suffocation, they have a similar a line graph between the years, and the only difference is that the fire, flames, and smoke one, it kind of flipped, where the ages from 0 to 20, it spiked in 2000, where it's nowadays spiking at around age 60. And starting our first analysis, we'll be using regression analysis. And first, we'll be analyzing and interpreting the relationship between the age and causes of preventable deaths in 2020, and repeating it for 50 times and selecting the lowest AIC. So what I meant by this, I didn't mean lowest degree, but the lowest AIC value will determine which degree we'll be using, and comparing the model, that model, using smooth splines and cross-validation. So we'll be comparing the polynomial regression model and the smooth spline model, and constructing a fitted curve over a scatter plot, and seeing how they fit in the graph. And the null hypothesis for this is that there's no relationship between age and the cause of death, and that the age is the predictor and cause of death is the response. Continuing on, for poisoning, the degree that was used is 23, because AIC was the lowest AIC value between 1 to 50, which is 1,110. And as you can see, the cross-validation criterion, well, between the two criterion, the cross-validation one is slightly lower. So in this case, the smooth spline is a better model for this case, but either one is fairly accurate. As you can see, the R squared is fairly high. And the p-value in this case is less than 0.05, as you can see over here. And so there is a relationship between the age and death by poisoning, and we reject the null hypothesis. For motor vehicles, the criterion between the two criterions, the cross-validation one is significantly smaller than the AIC. So the smooth spine model is a better representation, again, for this model. And the polynomial regression model used for this was the degree on the 35th degree, where the R squared is 98 or 0.98, and the p-value is larger than 0.05. So there is no relationship between age and the cause of death, and we accept the null hypothesis. And as we could see a similar between this, continuing on, AIC value, this one's fairly close between the two, but the AIC value in this case is the better model since it is lower, and the degree is the 20th one, and the p-value is larger than 0.05. So there's no relationship between the two. For choking, the cross-validation value is smaller, so the smooth spine model is better in this case, since there's a significant difference between the two. And as you can see, the cross-validation one generally has a better way of predicting the plot compared to the polynomial regression model. And this, for this one, the p-value is less than 0.05. So again, there is a relationship, and we reject the null hypothesis. For drowning, the smooth spine model for this one is the better model, since the cross-validation value is smaller, and the R squared, as you can see, is still fairly high, and the p-value is larger than 0.05. So there's not really, there's no significant relationship between age and drowning in this case. For fires, flames, or smoke, cross-validation smaller than the AIC value. So smooth spine, again, is the better model for this case, and the p-value is less than 0.05. So we reject the null hypothesis, and there is a relationship. And the same for this as well. But this is a very big difference between the two, which is surprising to me. I always expected the cross-validation one to always continue, but in this case, the polynomial regression model is a better model to use for this cause of death, and the p-value is less than 0.05. So there is a relationship between the two. And moving on, for the next analysis, final analysis is the ANCOVA, and we'll be analyzing the relationship between changes over the years 2000 and 2020. And for time's sake, we'll mainly be analyzing two causes and representing the results, or presenting the results for the rest. And the two causes will be poisoning and motor vehicle. And the null hypothesis for this case is that there's no significant change over time, and the same predictors in response. Okay, so for poisoning, I transformed the data slightly to get a better R squared and a more accurate QQ plot. As you could see, the QQ plot in the transform data using the square root function is less skewed than the original one, and the R squared is higher, slightly higher, 0.83 to 0.87. And the p-value in this case is less than 0.05 again, and there is a significant change over time with this case, but by this cause of death. And well, from the previous graph that we've seen from the beginning, we could already see that there is a significant change over time. Continuing on, for motor vehicle, we generally did the same thing, but this time we transformed it using the logarithmic function, and the R squared, it has a significant change this time. It's from 0.69 to 0.80. So this is an accurate representation of this change. And you can see the QQ plot is less skewed from the previous one as well. And the p-value this time is actually larger than the 0.05. So there is no significant change. And we can see this from the plot that we've seen from the beginning as well. There hasn't been much of a change, just slightly. And moving on for conciseness and time's sake, the falls and choking, the p-values were less than 0.05, and there wasn't like a big significant change over time by these causes of deaths. And then the rest, there was no significant change since the p-value was larger than 0.05, which actually was surprising because I expected the choking to have have no significant change, whereas the fire flames folks to have change. But it's possibly due to the age group. That's something that I would love to focus on in the future. But I guess the data analyzing only the deaths and only ages from 0 to 100, it's just the data, if that makes sense. And finally, in conclusion, there is indeed a relationship between age and causes of preventable deaths by poisoning, choking, fire, flames, or smoke, and mechanical suffocation, but none by motor vehicles, falls, and drowning. And there is a considerable change over time for deaths by poisoning, falling, and choking, and none for motor vehicles, drowning, fire, flames, or smoke, and mechanical suffocation. And yep, that'll be all for my presentation. Thank you for listening.
So does anyone have questions to Tauhid?
If you ran your data across, is it fairly close to, is it against a normalized population, or is it a uniform total number of deaths against, is it close enough to 100% if you stack them all up? Or it covers some percentage of the expected.
Yeah, that's a good question, but I didn't really, that is something that I should have done in this analysis, but possibly I honestly I'm not sure how to answer that question.
Okay.
Yeah.
When I was looking at this, a couple of things that came to mind to me was with a small, you get a small enough population that there's not that many 120-year-old people. So to me, even the overall counts, that's why I was wondering about normalization, almost like the 20%, of the people who died at age 100, there might, there's a small number,
small number.
And
yeah, go ahead. Sorry,
so
I think that's a reasonable question. Yeah, that's a reasonable question, but certainly, 2000 and 2020, not big population difference. So I think still it's reasonable to use counts here.
The actual data was from like 1999 to all the way to 2021. So that's like definitely somewhere. And they also had like an age group, but I kind of completely like deleted that because I felt like it would be a little bit more complicated, but that's something like that would be helpful to answer your question, because then it'll separate. I don't know how to explain it, but it's just a theory. But like I guess for further analysis, we could or I could separate age groups and compare like the younger and older ones and stuff like that and see from there. I don't know if that.
There's lots of ways to cut these data. But I liked what I saw.
Thank you.
And definitely gave me something, but was kind of started thinking about other stuff about it. So yeah. Thank you.
Thank you.
Do you have
I
any?
was curious.
Yeah, go ahead.
Yeah.
I was curious how the causes of death were selected for your analysis, because I thought you said at the beginning that the variables that you had selected were just part of the whole data set.
Yes. Yeah. That it was from the. Hold on, let me see if I could. I didn't really read too much into it, but that's like this is like generally what the NSC website used for the data set and what they analyzed on their part. These are the causes of that they only had. There wasn't like anything else from there. There probably are more, but that's generally what they use. There's probably like more, but like they're probably like not as significant as these are.
Right. I just didn't know if you had done the selection yourself.
No, I've got it from a website.
Yeah, I put the
Like
link
a
to the
healthcare
website in the chat.
Yeah.
Any other questions? Sorry, just I would like to confirm a couple of things. So you said the motor vehicle deaths that you don't have the age trend if you fit the linear model.
Mhm.
What is the I mean, in the conclusion, you said that for motor vehicles, we don't have any age trend, but that means no linear trend, probably. Can I see the graph for motor vehicle death?
Which one? This one?
Motor vehicle. Oh, this one. Yeah. So
I'm not.
we have, yeah. So we have no linear trend, but certainly,
No linear.
you know, age 20, it's much higher. Yeah. I see.
So it's like it spikes like sometimes for some cause of that. There's not really like any like you said, like a trend.
Yeah, but if you
But
fit
there is
the
like sites.
more complicated curve, suddenly age can explain some of the part. Yeah, I see. Yeah, it's interesting. And the analysis is very interesting, and it's hard to find this kind of topics that for which the polynomial regression is very useful. Usually even the polynomial regression with degree 2 is often not useful for most of the data. So I think you found a good data. And the only one suggestion I have is you applied the polynomial regression with usual, the basis like x and x square and x cube. If you do orthogonal basis, probably you have less, singularity problem. I mean, the multi-collinearity problem. So probably you will see less, non-estimable coefficients for higher degree polynomial. Yeah. So that is some options you can change, but except for that, it's very interesting analysis. And certainly, life insurance company estimates this kind of thing all the time. So I think there is a rich literature from maybe 30, 40 years ago until now. And it's surprising that this kind of, accidental deaths do not really decrease over the last 20 years, even though we have much better technology. So that's really
surprising how poisoning and poisoning is like it's still like the same, but like it's still around
even
that age.
Much higher, right? So
significantly higher.
Yeah, that's terrible situation.
Yeah.
Okay. Yeah, that's interesting. Yeah.
Right.
Does anyone have more questions? Okay. Yeah, it's great. And yeah, so the next one is so James, can you share the screen?
Can you see my screen?
Yes, yes, you can start.
So I did my final presentation on trying to predict House and Senate election results at the county level. My objectives for the project were two. One, to summarize predictive variables using principal component analysis, and also to compare models for House and Senate election results at the county level, using logistic regression models, principal component regression tree, linear discriminant analysis, and quadratic discriminant analysis. My data sources, the House and Senate vote results come from the link election lab at MIT.edu. They have data sets for 2016, 2018, 2020 for different types of elections at the precinct level. And for the county level data, I got that from the census using the TIDI census package in R to make API calls to the Census Bureau. And for my training sets, after doing the principal component analysis, reduced the number of predictors to 37 for the House and 36 for the Senate. And it was down from about 70 beforehand. For the test sets, because for the test set, I used the 2020 House and Senate elections, and I used 2016, 2018 for the training set. So that's why there's less observations for the test sets. So the categories that I use for predictors, so for age, it was the percentage of the population in different age brackets. For gender, I used the percentage of the population that were female, percentage of the population in different race and ethnicity categories, percentage of the population that's foreign born, or those that are at veteran status, those that have a disability, the percentage of the workforce that are in the armed services, the unemployment rate for the county. For industry, it was the percentage of the workforce in different industry groups, such as agriculture, like fishing and mining, or education, or the arts. Employment types, percentage of the workforce that are self-employed, or those that are wage or salary employees, or those that are for the government. For income, for that group, I used percentage of the population working, percentage of the population in different income brackets up to $200,000 or more per year. For household income, I used the median household income. For poverty, I used two measures, one for predicting, or one for the percentage of households that are at or below poverty level, and the other for the percentage of individuals that are at or below poverty level. And for education, this was had many groups for it. One part was like the highest level of educational attainment up through like graduate school and beyond, and another part was two predictors, the percentage of population over 18 who had a high school degree or equivalent, or those that had a bachelor's degree or equivalent. And these two graphs are just showing for the test set the percentage of the counties that have either Republican or Democratic vote majority. So we'd like to try to beat for the prediction models is 17.4%, less than 17.4% error rate for House elections, and less than 15.1% error rate for Senate elections. And these are a few scatter plots showing some of the general trends for some of the predictors. On the y-axis is the log of the ratio of votes for Democrats to votes for Republicans. So along the dashed blue line, anything below that line, there'll be where the majority of the votes were for Republicans. Anything above be for Democrats. And you can see that as the population is older, tends to more votes tend to go towards Republicans. And that was for the House. This is for the Senate. See that same kind of trend here also. And this is for the House. These are the categories before the predictors before doing the principal component analysis. These had the greatest correlation with that log of that same ratio. And you can see education seems to have a stronger correlation. And percent of the population working in agriculture or other industry. Also does too. I think it could be a good indicator for maybe a rural area, and also maybe for a professional area or professional for an urban area for percentage of population working in the professional industry. This is for the Senate. You can see same education and for the population works organic careers also, and as well as some race and ethnicity demographic data. And these are some scree plots for doing principal component analysis. I did choose 80% of, I wanted the number of components for each group to explain about 80% of the variance. And so it was somewhat arbitrary, but I was trying to really minimize the number of predictors that I had. What was interesting is for industry, no one principal component really explains quite as much as the variance as the others, which is a little bit different than you see for the other categories. And this is for the Senate data. It looks very similar to the House data. This is a correlation matrix for the House data after doing the principal component analysis. There is some multi-collinearity. What I thought was interesting too was for the percent of the population that are female. It has a strong positive correlation with first principal component for race and ethnicity, but a strong negative correlation with the second component. I just thought that was interesting. You can see the same here too for the Senate data. You can also see some multicollinearity. And so this is, I first started with legislative regression. And for the categories, you can see it's kind of hard to, a little bit hard to interpret with the principal components, but race and ethnicity had, all significant at the 0.1%. Same with income, insurance, education. For individual, for not principal components, percent of the population is female or foreign born. Percent of the population that are female for both the House and the Senate seem to have increased likelihood that a county will have more Democrat votes than Republican votes. And for legislative regression, I did use for the response variable just whether there are more votes for Republicans or Democrats. It's a binary response variable. And for just the first for legislative regression for the House, I got an error rate of 12%, AUC of 86.5%, and for the Senate, 11.8 with a AUC of 84. So it was pretty far below that threshold. And this is I did do a forward and backward selection of AIC afterwards, see if I could get a better model. Most predictors are significant. Interesting is there were two different predictors. I didn't do a principal component analysis on poverty levels on the two poverty measures. I maybe should have. One of those was dropped. And there were a few principal components from different categories that were dropped also. The model did not perform as well as the model that was not did not use selection of AIC. A little bit higher of an error rate for the House and also for the Senate. I did afterwards. I did a principal component regression. These graphs showing the number of components on the mean squared error percentage for those number of components using 10-fold cross validation. I did two. I used two models with different sets of components. The first one for both the House and the Senate. For the first one for the House, I used number of components that had the lowest root mean squared error percentage, and it was 63 components for the House. I should mention too, I didn't use the model that had the principal components. I used the model that the training and test sets before doing the principal component analysis. So it's with all those 70 variables. Had an error rate of 19.8%, which is pretty bad. Until it's higher than the the threshold that we set earlier. Afterwards, I'm sorry about that. Afterwards, I relaxed the trying to explain the model with 90% of the using the number of components that explained 90% of the variance in the model, which is averages that I picked. Better error rate 15.2% for the House, and for the Senate, use the same two decisions. Error rate 14.2% for the first model, and 10.6% for the second model. So both models improved quite a bit in terms of the error rate. Could show maybe there's some overfitting using the models of the lowest root mean square error percentage. I also did try to fit a model using a regression tree. This is for the House. It's a little bit hard to interpret with some of the the nodes using principal components. What's interesting though, on the right, you can see the percent of females below 59%. All the terminal nodes end up with value less than 0, and for the response variable for the regression tree, I did use the log of the ratio of Republicans to Democrats to Republicans. So anything below 0 would be classified as a like a county that Republicans had a vote majority in. For the error rate, 15% for the regression tree. They did the same test and training mean square error. I did not prune the tree. The number of nodes, the 15 nodes were for the regression tree for the House, and it was the same number of nodes with the lowest number of cross-validation errors. And this is for the Senate, a little bit harder to interpret. The terminal nodes all either terminate with a principal component, or if there isn't a principal component, they're both indicative of a Republican vote majority. We have the same train and test mean square error for the Senate regression tree. And again, the number of nodes were 16 nodes had the lowest number of misclassifications. Added also linear discriminant analysis. This is for the House data on the left and the Senate, the House set on the left and the Senate set on the right. You can note that percentage of the population are female, or higher percentage of the population that have disability, or those in the armed forces, or like a higher median income, all tend to increase the probability that it's going to be a Democratic vote majority. And you can see that in the Senate, in the Senate set too. If we're doing the linear discriminant analysis in the House, got error rate of 12.3 and 12 for the Senate. And also did quadratic discriminant analysis for the House and the Senate, and got error rate of 12.6 and 12.2 for the House and the Senate, respectively. In summary, the best model for the House was the just logistic regression without selection by ASC. And
14 minutes.
For the Senate, using the principal component regression with lower number of components. In general, it's usually easier to predict the Senate elections, tend to have the lower error rate. But also, there's a lot of information missing. There's a lot more that goes into how to predict elections, economic indicators, things that are currently happening in the country. Or a big one is too is the midterm elections. I think may have helped explain why it was a bit hard to predict House elections. I think for future work too, add some of this information to that model, and also could gather some data for the House and Senate elections for 2022 and see if can predict a better model with 2020 data in the training set too. Yeah. And that's it. Can I answer any of your questions?
Okay.
No,
Go ahead. Yep.
I don't know. It was very good that the analysis is there. So not a lot. I don't know whether or not anybody would be interested in that or not. Sorry, wrong. Thinking of too many things. Nice job. You know what? I'm going to stop my question and see if I can rephrase it before I'm just gonna mute.
Sorry, I have some question about the how data are used. So, for example, like the slide 13, I think the just the dimensions and the percentage of explained variance, and yeah, I think that the bar graph of percentage of explained variance. Yeah. So what does, or maybe one page before, sorry. Yeah. So what does that mean? The dimension for age. So age is one variable, right? So continuous variable, I thought. And what dimension means? So what did you do with the data?
So I use the group. So for the like just like the variables like in the age category, I had it separated to like the percentage of the population like in each age bracket. And I did a principal component analysis on just that group on the response variable when it was the log of the ratio of Republicans and Democrats. And then like for that, so the
I
the
see.
principal
So
components that I used.
basically, okay. So basically, the for each age bracket, percentage is given for each county. So that's why you summarize by principal component.
Yeah.
Okay,
Yeah.
I see. And sorry, and also, can you summarize the which of the error rates are trainings error and which are test error? Obviously, you know, the tree regression, you put the test error and the training error maybe side by side, but generally the error rate are training error.
Generally, generally it's all test error.
Test error, okay, for cross-validated sets.
I didn't do cross-validate. I just used the training set was the
training
data
versus test. Okay, what percentages are in training, and what percentages is for test?
It's about 2/3 and 1/3.
Okay, I see. Okay, I see. Okay, thank you. Yeah, the analysis is pretty comprehensive, and yeah, it's interesting that the CNAT is easier to predict. What's the reason behind it?
Yeah.
Maybe the proportion of seats. Maybe North Dakota, it's easy to predict, but maybe for larger states, it's harder to explain. I don't know why that's true, but yeah, that's interesting. Okay. Does anyone or any dog have questions?
Yeah, sorry, I have 2 dogs with me right now.
I like dogs. Yeah, it's a very interesting question and comprehensive analysis. So yeah.
Thank you.
Yeah. Okay, so the last one is, I think, the Erica. Yeah.
Hi, just a heads up, I'm apologizing in advance because I'm not feeling well and I kind of have a cough, so you may hear me coughing in your ears, or I'm going to try to mute myself if I do cough, but let me share my screen. Okay, so I did my project on train accident classification. What I'm going to be going over today, just an introduction to the data I used, some of the models I ran and comparisons, and then the results and some ideas for future work. So just starting off the introduction, I got this data set from the Department of Transportation, and it's said to contain any reported cases of collisions, derailments, fires, explosions, acts of God, or other events involving operation of railroad on-track equipment. All this data ranges from 1975 to 2022. And when I initially pulled it, it had around like 200,000 observations and 160 variables. Out of that 160, these are the ones that I felt were interesting. My response variable is going to be the accident type. And then some of my predictors are the milepost, which is basically how far away the train was from like the latest junction or train station that they visited, the temperature, weather condition, train speed. I'm not sure exactly how you say this, but I'm going to say it's gross tonnage, and that's supposed to be kind of like the volume of the whole train. Passengers transported, that's just a binary yes or no. The month, the hour, and then I created this variable called NA test. And as you can see right under it, there's something else called number of positive tests. So sometimes when there's train accidents, they would test the train crew members for drugs or alcohol, but that wasn't every single time. So there's a lot of those entries that were just empty. So I created a variable for if there wasn't any testing. And then I also kept all the ones where there were any numbers of positive tests. And then I created these variables, loaded cars and empty cars, because they originally just had them split out by passenger or if they were freight cars. And then this is just a correlation matrix between all of my numerical variables, just to kind of show that there's a good starting point, because I feel like not a lot of these are super correlated, except for the loaded cars and the gross tonnage, which I feel like makes sense because if there's more cars, there's going to be more volume. And then there's just other stuff like the temperature in the month makes sense, maybe like temperature an hour, empty cars and the train speed, or if there's loaded, maybe if it's loaded, it can't go as fast, or if it's empty, it can go that faster, just stuff like that. And then into some of the dating cleaning that I did, because I did not use all the observations that they had. I took out about 172 because there was these two accident types that had less than 1,000 occurrences. And that was the explosion detonation or the railroad grade crossing. I just felt like because there was such low occurrences of them that they probably wouldn't be super helpful for the analysis. And then I also removed about 20,000 observations that were just belonging to an accident type of other. I originally tried to use that, but I feel like without it, it was a lot clearer in the categorization. So I feel like because this is kind of an outlier accident type, I just left it out. And then I also had to remove about 400 observations just because they had some NAs in the fields that I was interested in. And so I ended up using, sorry. So I ended up using about 190,000 observations for my analysis. So this is just a visual kind of showing the different accident types and how many occur in each category. And as you can see, just from looking at this, the derailments pretty much dominate the data set. There's about like a 2-to-1 ratio. So like 2 derailments for every single other type of accident. And so one of the ways that I try to mitigate this problem, because in classification, if you just have like one class that is a majority of the data, your classification models are probably just going to keep guessing that and get it like supposedly correct, just because it's easy to guess something if it happens like 90% of the time. So how I tried to eliminate that was by doing something called undersampling. And what I decided to do is create 2 extra data sets other than just a full data set. One of them, I did like a 1-to-1 ratio between the derailments and the next largest class, which is collisions. And then another one, I did a 1-to-2 ratio with the next largest class, so that collisions would actually be the most prominent in the data set. And derailments would be closer to some of the other accident types. And kind of just talking about why I feel like this analysis could be interesting, because it is kind of weird that the data set only has occurrences like of accidents. There's no other information about when accidents aren't happening. But I feel like you can use that basically, if you are going to get an accident, you can see like on what kind of conditions you're going into. If you are going to get into an accident, what could be the most likely. And maybe that could be useful for railroad companies to just kind of build some like precautions or try to, just like find ways around that to make these accidents happen less. And just showing this table because these accidents are very expensive. They're, on average $60,000 or more. So that's quite a chunk of change. But getting into the models that I ran, the first one that I did was multinomial logistic regression. I did AIC on all these 3 data sets that I discussed. And the only one that had any variables removed was my undersampled data set 2, which is the one where the derailments happen with a 1-to-2 ratio of the next largest accident type. And then you can just see based on this table, like I was talking about earlier, if you use the full data set where there's one class that pretty much dominates it, you're going to get really good accuracy. Just because it's super easy to guess the most common thing. But if you kind of split it out more to try to see if it works better for more like of a generalized data set, you can see that the accuracy is a lot closer to around 60%. And yeah, these are all accuracy numbers. I did not put error rates numbers in there. Sorry, I probably should have labeled that better, but yeah, so I just did training accuracy test and then also like a 5-fold accuracy of each of these. And then the next thing that I wanted to try was linear discriminant analysis, because I saw that there's kind of a way where you can try to evaluate a data set that has one class that's more dominant by doing something other than just an error rate or an accuracy rate. And how you can do that is by doing something called 1 versus rest ROC and the AUC calculations. And how this is done, excuse me, how this is done is you kind of like force a binary classification by taking one of the cases or one of your classes and labeling that like your positive case, and then taking every other class and making that like a negative case. So you just have like one class versus everything else. And then you do your binary classification that way and get your ROC and AUC. And then you do that with every single class versus the rest, and then you average those AUCs. And you can see just from looking at each of these, the AUCs are really low and the average is really low, which is something we would kind of expect, because even though the model can classify really easily because one class is more dominant, it's not actually necessarily a very good model. It definitely will not generalize well. So I feel like this shows that, because basically the baseline is at 0.5 and we're at 0.58. But then looking at the 2 undersampled data sets that I did to get a better representation of actually making these prediction about accident types, you can see from the first undersampled data set where there's a 1-to-1 ratio of the derailment and the next largest class, which is the collisions. The training and testing accuracy are both around 60%, which is very similar to the multinomial linear regression. And I just included these contingency tables. And I feel like just something interesting that you can see is even though the derailments are just as common as the collisions in this data set, it still seems to choose derailments majority of the time across all of the accident types. So definitely probably a lot of those predictors are pretty prominent to indicate if there's going to be a derailment. And then this is the same thing with the other undersampled data set, which has the 1-to-2 ratio of the derailments in the collisions. And then you can see that it's picking collisions a lot more often. Right here. And that kind of coincides with what I've been saying, just how if there's one case that dominates the data set, it's probably going to guess that majority of the time. But yeah, this one had a little bit better performance. So the last method that I tried was just doing something tree-based because from what I understand, classification trees can be good for unbalanced data sets. So I tried to do these classification trees with the cross-validation and pruning on the full data set and the undersampled data sets. And it's pretty consistent with everything that we've seen before with the training and test accuracy, which I feel like is surprising because I feel like the tree-based method would be better for this, but I feel like what's more interesting than the accuracy is actually looking at the trees. So this one's the one on the full data set. And you can see that the train speed and the gross tonnage seems to create a lot of like dividing decisions for what kind of accident it's going to be, even though like we had seen a lot of the times, it's just going to pick derailment. And then I just chose the next most accurate model, which was the first undersampled set. And you can see again, like the gross tonnage and the train speed come up a few times, but this one also takes a look more at the empty and loaded cars and also the drug and alcohol testing. And it seems to pick derailment a lot still, but a little bit less. So a little bit more generalized. So just going over all the results, using the full data set really greatly affects the results as we predicted. And it seems like a lot of the models run on the other data sets seem to generalize pretty well, looking at how they're all pretty consistent, even across the cross-validation, like the testing and the training accuracies. So that shows that they generalize pretty well. And yeah, they all kind of produce the accuracy around 60%. And then some future work. I feel like it'd be really interesting to go in and look at the coefficients and the variables for the multinomial logistic regression and the linear discriminant analysis, just because then you can really get an idea of how these variables are really affecting what accident type it could possibly be. So I feel like that could be more insightful if someone was going to use something like this in the real world. And also, yeah, just kind of, I feel like I wrote the same thing twice, but also just trying with the classification trees to get a little bit deeper into it, trying to improve the performance by doing some sort of bagging, boosting, or random forests, just because I did not have the chance to do that, but I feel like that could be interesting to look at as well. But that's pretty much all I have for today. So let me know if you have any questions. Oh, Professor, I think you're muted, but I can see you talking.
Does anyone have questions? Sorry. Yeah. Yeah, I think that Erica handled the data very carefully. So basically, we only have positive cases in this data set. It's really hard to get some implication from the data set. But basically, we have several different type of accidents. So in my understanding, she uses the positive cases of other accidents as a kind of quasi-negative cases and to see what's the cause of each accident. And then, of course, the important thing is the proportion of positive case and negative case in the population, which is unknown. So we have to make some assumption But in such a case, we can do oversampling or undersampling. So typically, undersampling or oversampling is used when our data is different from population. So typical case is like the medical data. So we have many patients' data, but not the healthy control data. Healthy control data is very small, even though in population it's large. So in such a case, we have to repeatedly use those healthy control data. So that is oversampling, or we undersample the patient's data to make the ratio to a reasonable range. So I think that's what Erica did. Yeah, and I think it's pretty reasonable. And some complication when we use oversampling or undersampling in tree-based regression. I think the tree-based regression is not really likelihood-based. So sometimes oversampling, undersampling affects the results. It it works better in some cases, worse in some cases. Does anyone have more questions?
She was very clear overall.
Thank you.
Yeah, actually, I thought that this data is a little bit hard to handle, to get implications. But yeah, I think you used really good strategies to analyze the data.